So, I think that one concurrent viewer is myself. Give it a minute for it to drop. So welcome and hello, hope your day is going well. What we are going to do now is continue. Yeah, I think that was me. Continue studying Clojure. We're making headway, we're almost there. 67 problems in. I did about 10 more again at work. Wow, it's taking me like 10, takes me a whole day to do 10 problems. Just crazy, but kind of has more to do with, you know, I'm working at the same time. So it's like, you know, I kind of talk a lot to my coworkers, you know, being a social animal and all that. So I like talking, sharing ideas and whatnot. It's a good time. Anyway, yeah, I'm generally pretty busy at my job, so I guess it makes sense. But these problems aren't that easy either. They're kind of hard. They take time, and there's like kind of a lot to go into or go over with each problem. So anyway, the last thing we did before I went to bed yesterday, I guess it'd be yesterday, is we were looking at prime numbers, and we actually solved the problem. I built a sieve here. It's somewhat iterative, imperative, this style. It's not really as functional as you might expect. I'm not sure. Let's see if we run this. What were the other solutions? What they do? Oh yeah, the other solutions were kind of not as interesting because they would use like they wouldn't use the sieve. They would use like a what do they call that? They would use like the other algorithm, which is just check if everything below this number, if anything below it divides it, kind of a thing. That'll tell you if it's prime. Like more brute force kind of algorithms, which are a little easier to write. So I was a little less interested. This is a sieve, but this is also like kind of ugly. It looks like it looks like a sieve. What did he do here? Like let's find out. Let's see. Yeah, past primes. That was the other one too. I had suggested that, like just accumulating a list of primes you've already seen, and then that's sort of also like kind of brute force as well. It's pretty similar to the sieve approach though, but not really. The sieve is a little more efficient than this because this, like, you accumulate primes over time, whereas with the sieve you actually, the primes become further spaced out, and you actually eliminate larger and larger primes. I don't know how exactly to describe it, but the sieve is kind of efficient. I don't know how efficient exactly it is, but it's relatively efficient. Lazy sequence can drop while some. I don't think this is a sieve. What does this do? You've got the function, right? Which, oh, right, okay, you get a sieve of 2. This is an arity, multiple arities. Now if there are primes of n, or this is the, if you give 2 arguments, right, primes and n, so 2 and 2 is n. So you're going to cons n, so I guess cons 2, with a lazy sequence. So I think this is an infinite sequence. It seems to be potentially infinite. Let next be, okay, so he's using a keyword here, but he's going to overwrite the keyword with the result of something. So we'll get to that shortly. What that is the next, and then return. You ultimately return sieve of Also, holy smokes, look at all these. Conjoin primes with next, right? So this is the next prime. Conjoin with your set of primes, right? Here, and then sieve on, now that's kind of interesting, the next prime value. So this is the right, so this is actually an infinite sequence of prime values. This is actually, I don't think this is a sieve then if it's an infinite number of values. Yeah, this is actually going to go prime by prime. So taking x number of primes from this is an infinite sequence. That's why I use lazy sequence. Fair enough. Okay, so all right. So the really core of the code seems to be the next part, right? If you conjoin, so you update your primes, and you also update this, the result with this next prime. And when you take a certain chunk of this infinite sequence. So I don't know how that works. It's like, I guess it probably just executes, the first few iterations until you have as many elements as you wanted, and then it stops. Doesn't execute the sequences anymore. I guess I don't really know. I don't really fully understand this, but how this interacts, this lazy sequence. I know how not what the result is, but I don't know how it was programmed. It's kind of an interesting construct, complementary construct that's going on. Anyway, so this part's the interesting part. So it says next is going to be bound to this first drop while function. It looks like there's this function and some. Now this is not so clear, right? There's mod IP 0 function sum of primes 1, 2, 3 is the function. Yeah, so this sum, okay, what this is going to do is it'll return the thing that is true, that this is true for, the first one. So if you've got primes, say 0 mod IP, where I is the input function, input value, but you're going to loop through all of your primes, check against I, and say I modulo P. So basically this is figuring out, do any of the primes divide I? If so, return it, right? And you're going to drop while, it looks like you're going to drop while using this function, which, yeah, this sum goes all the way here, so this function, you're going to apply this function. So when this is true, basically any time that a prime divides I, you're going to keep dropping. So you're going to keep dropping the things that are not prime. And the thing that's interesting here is that you're also going to drop n from range. So this is the sequence that you begin with. So you begin with a certain starting point in this range. And basically, right, so you're going to just drop all the values up to the next prime that, yeah, drop all the composite values up to the next prime, starting from dropping increment of n number of things. So n is, I guess, your starting point. Now it's kind of weird here. Yeah, well, you're also dropping 0. I think that's the increment part. So like if you're starting at 2, you drop everything including 2 and 0. That's what's going on here. So it would start at 3 as an example. So drop while this is true, and then take the first of what's left over after dropping all these values. So that's kind of interesting. The problem, I think, with this, though, is that you're getting this chunk section of the range every single time that you call this function, which is extremely expensive. It's like if you were 1,000 elements in, then you'd have to drop 1,000 elements off of the range every single time that you want to get the next prime number. Drop 1,000 elements, drop 10,000, whatever it is, however many, and then you also need to loop through all the primes. But this is not actually a sieve. That's actually the bottom line, though. The important part is not actually the sieve, because you have to check. You have to perform a division for every prime divisor that you've accumulated up to that point for every single value. Whereas the sieve, it's only the prime divisors that actually are divisors of that value that you'll end up, iterating over that particular index, if that makes sense. So yeah, so this is a lot less efficient. That was kind of a lot, but I thought it said sieve, so I thought maybe it was the sieve of Eratosthenes proper, but it's not. This is like sieve-like, but not quite. Not quite. Okay. So the next thing here is, and there's a bunch of other solutions. I think people did kind of hack stuff for this. I think we went over this, and I was like kind of disappointed, but not too impressed, and somewhat disappointed. I do at least appreciate. Oh yeah, this is kind of cool. I do at least appreciate. I'll tell you what this does in a second. I at least do appreciate that that there's diversity of solutions here. Yeah, I can appreciate that, and then I also like my own solution. I think it's pretty good overall. This is very interesting. This, I think we talked about this too. This is actually this is all of the prime numbers that can be contained in 64 bits, and there's sort of an algorithm to generate these values very efficiently, but without using like a direct hash map. So pretty neat, but it has something to do. This is more of like a numerical thing. This has a lot more to do with, like, I don't know, just hacking together something that'll generate the first few primes. I mean, 64 bits is a lot of numbers, right? 2 raised to 64th that's a lot of primes. So this is pretty good as far as, like, for all practical intents and purposes. This is more or less, this will do it. This will get you where you gotta go with your primes. Unless we're talking like breaking SHA and something. So let's just look at SHA quickly. 256 and 512. So 32-bit words, 64-bit words. I don't know how big 512 and 256 output size in bits. 256 bits, 512 bits. Okay. So that's a lot of bits. That, to give you some idea how much that is. Oops. That's a lot. That's a big number. Right, so the prime numbers for the SHA 256 and 512 are enormous. And they use the difficulty of what do they call that? They use the difficulty of there's even other SHA versions, I guess. They use the difficulty of, I think, integer factorization. I want to say something like that, to create security. Yeah, to make it very difficult to decrypt the messages that you're sending. It's pretty cool. Apparently Shore's algorithm can decrypt these things, although it's extremely impractical to forgot what I was even saying. It's extremely impractical to do what? I forgot what I was even saying. Extremely impractical to actually perform quantum computing, especially if you're trying to do it on a mass scale. It's not reasonably scalable, as I understand it. So kind of cool. We're actually going to look at integer factorization in a bit today. Also, what did I name my stream for an hour? It'll be more than an hour. It's going to be for a few hours. We're probably going to go till like 9, a little after 9. Yeah. All right. Yeah, so that's a sieve. The way I did it, I did a normal sieve, but with n squared, assuming that I actually know that primes, generally speaking, are the number of primes that you're going out to. Like there's an approximation for how many primes there are given n, right? How many primes are less than equal to n, and that's something like n over log n, something like that. It's a little bit, it's sublinear, right? Like how many primes. All right, let's look at that briefly. Prime counting function, yeah. Yeah, so the distribution is about n over log n. The prime counting function is x over log n. So it's actually a little bit less than linear, right? Like slightly less than linear. And there's some right asymptotic bounds. Wow. So the Riemann hypothesis is conjecture most important unsolved problem in pure mathematics. Great interest in number theory. Results about the distribution of prime numbers proposed by Riemann. So apparently Riemann proved the exact prime counting function, and then that's also related to the Riemann hypothesis. Wow, that'd be cool to prove that. How these functions compare at powers of 10. Wow. Holy smokes. How many primes there are? Up to and including 10 to the 27th. How do they calculate those things? That's amazing. You know, what's interesting about the prime numbers, it's actually so difficult to calculate the prime numbers that calculating them very far out is really, really difficult. Like, you could describe the natural numbers easily to almost any size. Right, pick any arbitrarily large natural number and you can describe it. But something like how many, wow, that's very interesting. Somewhat easily describe it, I guess. Not necessarily, right? I mean, there's a certain physical limit how many digits you can describe. How would you describe extremely large numbers? I don't know. Maybe as a sequence? I'm thinking like as like a geometric sequence, maybe? No. I mean, that's effectively how we describe large integers now, is something like the coefficients of a geometric series or a geometric sum. But is there a way to make it even more compact than that? I don't know. I have no idea. It's an interesting question, though. How does one describe extremely large numbers? Like precisely. Well, certainly it's a logarithmic scale, right? If we use the geometric, coefficients of a geometric series of powers of 10, as an example, is not series, geometric sum of powers of 10, then you're looking at a something that's logarithmic in the number of the size of the integer. But can you do better than logarithmic? Yeah, I guess you could. You could do what do they call that? A trailing logarithm, a recursive logarithm, something that's a big O of a recursive logarithm, which is once you've got this set of digits that represents the geometric series, right? So, you know, like 1,350, right? You only need 4 characters, 1, 3, 5, and 0. Now suppose you were to describe that number using the same, in other words, the 1, 3, 5, and 0, those 4 digits, if you were to use the same approach. Is that possible? Can you do it that way? I wonder. You don't just count the digits, you would count. Right, 10 to the 4th is 10,000. So you use 4 digits and you can describe any number of size 10,000. Or no, so over, yeah. Well, yeah, any below 10,000, anything below 10,000. But the problem is, once you've represented it this way, 1350, how can you perform the same algorithm again? You lose information, I think, or it seems like you're going to lose information. I don't know. In theory, it can be done, right? I mean, in theory, it's 1350. You have 1 by 10 to the 4th, 3 by 10 to the 3rd, 5 by 10 squared, and 0 by 10 to the 1st. Excuse me, that gives you another number, doesn't it? Well, no, it doesn't give you another number. That's the problem. It gives you a representation of the number. So we can do logarithmic representations. But even still, you know, it could be a lot of digits. Representing a number in linear in the number of bits. That's effectively where we're at right here with this. I'm wondering if you can do something that's recursive logarithm in the number of in the integer representation. That's an interesting problem. Ooh, excuse me. Let's see if there's anything on the subject out there. Representing integers with less memory space. I get it, they're showing views in binary, but the binary representation itself, I guess, is a number. You can convert it back and forth from a binary representation to a base 10 representation. That's all well and good, but is it possible to encode a binary representation even further? Right? I guess you can keep changing the base. So from base 2 you can convert to hexadecimal, which is base 16, and use a fourth of the characters. Fourth of the space. The problem with that, though, is then you need to increase the number of the character table that you're working with. Double the character table, but drop the number of characters you use by a fourth, or no, multiply it by 8. So instead of 2, it's 16 different characters. But you drop the total number of characters that you need by drop the total number of characters that you need by a fourth. Alright, divide by 4. If you went to base like 64, which would be 64 different symbols, you have to know their values. That would be 4. So multiply your symbol table by 32, and And the 63 bits, first 63 bits would be, what was the first 4 bits? Gives you 0 to 15. That means 63 is first 6 bits, looks like. I mean, that's fine. 2 to the 6th, I think. Yeah. So you end up with a 1/6 of the number of characters, but now your symbol table is much larger as well, right? You double the symbol table, quadruple the symbol table size. Yeah, you get some pretty, what do they call that? You get some diminishing returns. You end up with some diminishing returns the more symbols you introduce. You don't actually save that many characters. I bet you 10 is the optimal. That's amazing, but I bet you that's the case. That because there's obviously an optimal where you have if you add the number of symbols plus the amount of space, number of characters that you need, 10 is probably optimal. Number of symbols you need to memorize, and I guess if you said from a binary representation, how many characters you would save and how much you'd increase the symbol table by, what factor you'd increase the symbol table by. There's a certain point where it's just not worth it. I think beyond hexadecimal, I think hexadecimal is probably like optimal too. It's pretty good. Cut it down to a 1/4, but also multiply the symbol table by 8. The symbol table is pretty small, so it's not a big deal. But anything beyond that, you're starting to, the symbol table doubles each time. Yeah, it's interesting. Hexadecimal and then base 10. I don't know if 10 is optimal, but it probably has some properties of it that are make it special. But anyway, even if you convert it to hexadecimal, there isn't a really obvious way to represent the number with less memory. To represent it exactly with less memory. Yeah, you're kind of stuck with logarithmic memory. Linear in the number of digits, and then linear in the number of bits. Is there a way to represent a number using less than the number of bits? I don't think so. I don't think so. Sum of powers of 2. So there may be a way to do better than that. Thinking that you get this vector that you can use as a dot product, which is fine. You can just use the vector itself, right? Which we end up doing. So like the 1,350 we know is a large number, but we only need 4 characters to represent it. But how about something that can encode that to something even smaller? Like even fewer bits of memory to encode that, to encode the encoding. You know, because you know that you've got a function from this 1350 to 1350, and you know how it works, but is there a way to go back the other way so that you can get those 4 characters and know exactly what they are? Unless you have some, I don't think you can. I think you could even prove that this is the best you can do, because there'll be loss of information if you try to compress it any further. Yeah, effectively any further compression would lead to something that's not a function, and so you'd have you could show that there's 2 different number representations that can result from the same input, and that implies that there's loss of information. Yeah, that's a law. You could show that's logically equivalent. I think logarithm and the linear in the number of bits is the lower bound. I think you can prove that. I don't know if you can, but it's an interesting thing to think about. I don't know if there's a formal proof anywhere. Maybe I can write a paper about that and go get a PhD. Free PhD. Easy peasy. Or maybe it's just trivially true, who knows. Anyway, the reason why I'm curious about it is because it's as if prime numbers have a special place when it comes to the representation of integers, because you sort of eliminate whole sections of representable integers, but you do it in sort of a harmonic sequence type of fashion. So first you eliminate half, then you eliminate a third, then you eliminate a fourth, then you eliminate a fifth, then every fifth, then you eliminate every sixth. And there's overlap over these as well. Eliminate every seventh, every eighth, every ninth, etc., etc. Well, it's actually not every half. It's not even harmonic. It's sort of this prime harmonic, and yeah, and there's overlap too. There's quite a bit of overlap of things that get eliminated more than once. That's the sieve of Eratosthenes, how that works. Pretty interesting. Pretty interesting. I don't really know if there's anything really valuable to be gained or to be thought of with all of that, but it's there. I don't know what to make of it. But anyway, the Riemann hypothesis is related to all of that too. It's the Goldbach's conjecture. Oldest and best known unsolved problems. Every even integer. Twin primes conjecture. Hilbert's 8th problem. Every even integer greater than 2 can be expressed as the sum of 2 primes. Conjecture has been shown to hold for all integers less than 4 times 10 to the 18th. Remains unproven despite considerable effort. Wow. Very cool. Anyway, so algorithms for evaluating pi of x. Simple way to find pi of x if x is not too large is to use the sieve of Eratosthenes. Produce the primes less than or equal to x and then to count them. More elaborate way of finding pi of x, that's what we used, is due to Legendre using the inclusion-exclusion principle. Given x, if p sub 1 and p sub n are distinct primes, then the number of integers less than or equal to x, which are divisible by no p sub I, is this floor of x minus this summation plus this summation minus this summation, where the 4 is the 4 function. This number is therefore equal to pi of x minus pi of the square root of x plus 1, when the numbers are the prime numbers less than or equal to the square root of x. Oh, wow. Interesting. Interesting. So if you can factorize x, then you can use Legander's watercolor caricature of Adrian Legander. The only existing portrait known. Not particularly flattering picture. Yeah. Okay. Okay, to return to what we're doing here. So yeah, there's a few ways to calculate the number of primes, but obviously it's a pretty difficult problem overall. Actually, part of the Riemann hypothesis is counting primes, believe it or not. So, but what I wanted to show is that you could see originally why I went into all that, down that rabbit hole, is that n squared is probably would contain all of the primes that include would contain the range that would include the first n prime numbers, because n squared is dominates n over log of n, which is roughly what we expect the distribution of primes to be. Also, I probably could have just used n instead of n squared for that algorithm to do the same thing, but I didn't. So yeah, I think so. I think it works like that. I think it can do it that way, or 2 times n, what have you. Okay. Actually, it's kind of an interesting question. If the number of primes is less, no, I think I would need to do it the other way around. I would actually invert that. I'd have to do log of n over n. No. I'm actually not sure, because if the number of primes, no, the number of primes less than or equal to n is roughly n over log of n. So if you want that's how it works. Okay, if you want the n primes, first n primes, then you've got to calculate, you multiply both of those things by log of n, and you get the first you get the first n primes. You would need a space roughly of n by log n. Right. Interesting. Whereas if you wanted the first n over log n values, then you would need the first n numbers to sieve through. Yeah. Confusing, but I think it works roughly like that. So you would need, so you could use something that's like, you do n by square of n, square root of n, or just n by like 2 log n, something like that, to give you a big enough range of numbers to work through. So I didn't actually need n squared to sieve through, but that's kind of beside the point. But that's how I know that n squared would be sufficient. But obviously, you performing that over n squared is extremely inefficient because n squared is a very large space to go through. So anyway, so this just introduces recursion and asks us to calculate what this result would be if we looped here, and it's just 76543. The reason being, this result gets conjoined with, this is the initial result, while x is greater than 0, you're going to decrement x and conjoin the result whatever x is plus 2. So that means that you're going to have 7 will be here, and then this is going to drop all the way down to 1. 1 plus 2 is 3, so you're going to have 7, 6, 5, 4, and then 3. So there you go. So let's go to 69. So merging with a function is an interesting question, a little harder question. What they're suggesting is, okay, write this function, the merge with, your own implementation of the merge with function in Clojure. So I got merge with 2, and we're going to reduce. This is a little complicated, what it does. It's not that complicated, but a little bit. Basically, I said, okay, we're going to reduce with a function over all of the maps into a single map, right? And by the way, the merge with, the way it works is, normally if you conjoin multiple maps together, if they share keys, then the last map that you conjoin with the shared key, whatever value is associated with it, as example, like 1 and 3 and 1 and 4, you merge those two. If you conjoin them, the 1 and 4 would overwrite the 1 and 3. So at key 1, you'd have value 4 rather than 3. That's the result of conjoining. Merge with says, okay, when you have these conflicts, like you have merging 1, 3 with 1, 4 at key 1, maybe you want to multiply the two numbers or add the two numbers or just do some function with these numbers. You can do that. That's what merge with does. It takes a function, and instead of simply overwriting at that key, you apply the function to the two values and then use that result to write at that point, at that key. What you end up with is, so the way to implement this, first thing you want is a check that it is a function that you're looking at, this f. And the way I did it, I said, okay, let's reduce over all the maps, and we're going to push our results into a blank map, right? We're talking Clojure here, which is a functional programming language, so we're going to get a new map anyway. So let's push all of these maps into a new map, and the function that we use is going to consider two different maps, which is our final map and the map in consideration. And then what we say is, okay, given this result map and a new map, we're going to reduce again over these two maps, right? Where you have the resulting map and the map that you're considering now. So what happens here is basically, first you're considering a map and any number of maps, a sequence of maps, and then now you're looking at just one map and this resulting map. And then what you want to do with these two maps now is say, okay, perform a second reduce, and you're going to say there's this current, what we're looking at so far, and then there's this key value pair in the map of interest that we're looking at. So we're sort of like we're looping over all the maps here, and then we're looping over up the key value pairs of a single map here. And then you say, okay, we're going to write to the map in a special way, the current map with the particular key value that we're interested in. And we're going to say, if we've already got this key in the map, then we want to perform this function on the inputs, which is get what's already there at the map, at that key, and get the value that we're interested in right now for this key value pair. Perform F on that, and that's what we're going to associate to the key. Otherwise, this if, otherwise, just use the new value, right? So this only happens when there's a conflict, and then so you perform that reduce over whatever you've currently got, this resulting map, and then the new map. So logically speaking, like pretty simple, pretty straightforward what it does. Like does kind of exactly what's asked, and then obviously we loop over do this for every map in the maps list. Done. Pretty easy, relatively easy. I'll just take a moment to explain that though. So 60 notes go to 70. Word sorting. This is kind of interesting. So it says write a function that splits a sentence up into a sorted list of words. Capitalization should not affect the sort order, and punctuation should be ignored. So have a nice day becomes a day have nice. So you ignore this capitalization at the beginning, which I found out actually if you try to sort on strings in Clojure, the capitalized letters strings will come first because capitalized letters are, I guess, sort of in terms of ASCII, if you compare like ASCII characters, they have actually a smaller value. Technically, there's a 32. There's a 32. The bit that represents the integer 32, so 2 to the 5th, that's added in the ASCII encoding to go from little h to big H. So anyway, the way to do this is there's a few ways to do it, but I'll show you what I did. Well, this isn't what I did originally. Actually, this one I got from someone else's solution. But what they decided to do is use a regular expression sequence. So basically, this searches sequentially for the given regular expression and creates a sequence out of that, that iteration. So this W is shorthand for shorthand for the lowercase alphabet letters, uppercase alphabet letters, underscores, and digits. So any of those values, this will match. And then this just says match at least one, any number of them, but at least one. And one or more. And that means that it's going to match only the words and none of the punctuation marks. And it'll just match one at a time, right? So you end up with this you end up with this set, not necessarily sorted, but you do end up with what you need, the pieces, and then a sequence that you need, a piece that you need, and then you sort using only the lowercase form. So it says sort by. It's going to consider only these. It's going to consider these values as lowercase when comparing to each other. So it ignores this capitalization, and then sorts appropriately. And that's what the sort by does with a function. And note this is called the last thread macro. And what this is going to do is it's going to call this function first with this value all the way to the right as an argument, and then it's going to use that result and push it all the way to the right of this function as an argument, and then call this sort. So it'll call the resequence and then the sort by, and then that gets returned, and you end up with the desired solution. So let's go to 71. Oh, wait. 70. Oh, I guess I didn't solve 71. Oh. What happened? I don't know what happened. Okay. I guess I just didn't. Oh, it's 171. Oh, okay. I mean, okay. Is there 72 anywhere? 73? I don't know. All right, so I'm assuming. Hold on, what? Maybe it's on the other page. 71. I don't know. I don't know what happened to 71 and 72, but there's 73 here at least. All right, I guess we're not going over 71 and 72. So this was pretty cool. I'm not going to show you the answer yet, but this is a really interesting problem. This is, I guess, one of the first hard problems we came across as well. See, this is hard. So we get an idea of what it means to be a hard problem on the 4Clojure site. So a tic-tac-toe board is represented by a two-dimensional vector. X is represented by keyword X. O is represented by keyword O, and empty is represented by keyword E. A player wins by placing 3 X's or 3 O's in a horizontal, vertical, or diagonal row. Write a function which analyzes a tic-tac-toe board and returns X, keyword X if X is 1, keyword O if O is 1, and nil if neither player is 1. So pretty standard question you'll get when it comes to computer science. This problem actually is one of the problems that you'll be asked if you take the TripleByte interview quiz and their interview process, go through their interview process. This is definitely an interesting question. Yeah, and it's asked rather frequently, and the solution that I came up with is actually really elegant. I've done this problem so many different times in so many different ways, and every time I do it, I think, kind of poorly. But what we're going to do is pretty interesting. I'll explain it before we look at it. I did actually steal this from someone else's solution, almost verbatim. The way that I did it originally is I said, okay, write a function that evaluates the horizontals, then something that evaluates the columns, the horizontal rows, then evaluates the columns, and then something that evaluates the diagonals. What I didn't think to do, which is what we're going to explain shortly, and that was pretty involved, the code for that. It was broken down into pieces, but it was very it was just very let's just say involved. Just there's kind of a lot going on, kind of unnecessarily complicated, I guess. You could break this down even to make this even simpler and just say, okay, look, we just need to take the groupings for each of these things, right? And then what we can do is say, okay, if we take the groupings of each of these things and then create a set out of the values there, and then say if the set is of size 1, that means that everything was equal, right? One of the things is doing an equality check to check that all of the values are the same. That's easily solved by inputting all these values into a set. So what you can do, in theory, is gather up all of these sets of 3, right? All the rows, all the columns, and the 2 diagonals, and then perform that set operation on each of those to determine which of them, I guess, have the same value all the way across. Filter what's left over for only the ones that have 1 left over, right? So it would be either empty or X or O or filtered out. And then once you've filtered everything out, you could say, okay, give me the first of what's left over, the first set that contains either an X or an O, right? And the first set that contains either an X or an O, you'll just return that, the X or the O, right, depending on what it is, the set. And this actually ends up being an extremely elegant solution, and I'll show you what that looks like. That's the approach. And so what it looks like is get the columns. The way you get the columns, you apply, you use the map function with a list as the function that you apply, and then you consider board to be a because it's a sequence of rows, you're going to use the supply function to actually use that sequence as arguments, right? So there'll be 3 arguments rather than 1 argument, and the arguments will be the rows themselves. And what this is going to do, this map function, map actually takes a function and applies it to the collections that are supplied to map, but it does it in a sequential way where it'll take, if you have three different rows as we're doing here, it'll take the first element of each of those rows and supply that to this list function, which obviously will just generate a list out of those 3 elements. And then it does the same thing with the second elements of each of the rows, and then the third elements of each of the rows. So you get exactly a sequence of columns, of the columns of the board. Pretty succinct way of doing that here. Then you can get diagonal forward, diagonal backward. This is kind of cool. We'll go into that in a second. And then finally, you can gather up all the possibilities by concatenating each of these sets of each of these sequences. So this will give you all the rows. This will give you all the columns. Concatenate will put each of these elements in this sequence become elements of this sequence, or the return sequence. And then finally, the diagonal forward, diagonal backward, you need to put it into a collection to sort of work properly with concatenate, because each of these aren't collections themselves. They are sequences, but they're not a sequence of sequences, whereas these are sequences of sequences. So you want to put this into a sequence, and then use concatenate on it. That's why you have this extra stuff going on here. Otherwise, it would be really confusing if you didn't have this. What it would do is you would take sequences of sequences, sequences of sequences, still a sequence of sequences, and then a whole bunch of elements that are just kind of scattered in there, which are not actually sequences. And then these, the way you get each of these is pretty clever too. You map again over, now the way it works is you map over the board and over the, let's actually start with the bottom one, so to get the backward sequence, you map over the board and the range of the count of the board, so 0, 1, 2 of the board is size 3. And what you do is, so map, we already said, is going to take the first 2 elements of these 2 collections. So it's going to use the first row and an index 0. And what this does, this function, is it applies to the first element, which is the first row, uses that as if it were like a map, and then gets at the index, which is index 0 of that row. So you get the, oh, hold on a second. Oh, okay. Okay. So right. So you end up with is the first row and the 0th index, which is the first element of the first row, and then obviously the second element is the second row, and you get the 1 now, which is the first index of, or the element at the index 1 of the second row, which is obviously the second element of the second row, and then finally index 2 would be the third element of the third row. So it's a very clever way of getting the backwards diagonal, and then as it turns out, you do the same thing in the other direction by just reversing the indices that you're grabbing out of each row. It's a very clever way to get the forward diagonal and the backward diagonal. And so yeah, so you can get the columns, forward diagonal, backward diagonal in a very succinct way, and then concatenate all those to give you all the possibilities, which is exactly what I was describing before, all these different possible groupings of 3. And then what you do is, again, similarly as described, map each of these values, these sequences, into a set, filter out all the sets that filter on only the sets that have one element. So these are the ones that have the same element in all 3 spots, and then you're going to concatenate all of those sequences into sort of a giant sequence. Now I think the idea here behind this concatenation, I'm not entirely certain, but I think what it ends up doing is, I see this part I got sort of stuck on and confused about when I was testing what actually ends up happening. Let me show that, what that looks like. As an example, if you've got these sets, the size 1, yeah, okay, so it does what we want, which is basically take the elements out of these sets and place them into a sequence. What'll happen then is, so now we got all these different sets of size 1. We concatenate, we pull all those keywords out into just one giant sequence of all of the values of that we found were sort of quote unquote winning possibilities, and then we just iterate over that sequence. We say, okay, the function we're going to use the sum, which does we look at we use this to check the sequence, and with each so what sum is going to do is the result of all of this is going to end up as a parameter to the right side of this, an argument to the right side of this, and we're going to apply this function on every element, and if it's true, then we return that element here in sum. If we don't find any of them, if none of them work, then we return nil, or we don't return anything. And this function, what it does, it says, oh, just check for that value, is it in this set? And this set is just an O and an X. So if it's in this set, if it's an O, right, O is in this set, this will return O. If it's the X, then it'll be in this set, and this will return X. And so then this will check that if any of the winning sets were an X or an O, and it goes sort of from left to right, which is kind of arbitrary. Obviously, if you have a winning combination for both O and X, in a real tic-tac-toe game that should never happen, so it doesn't really matter, but technically this could pick either one sort of randomly. This doesn't really say one way or the other which one it's going to pick. But if there is a winner, then it'll definitely pick that, and if there's no winner, then you have nil. So you have a very succinct, kind of concise way of solving this problem. And I thought this was very clever, and I'll remember it for the future. If I'm ever faced with this question again, figure out who won on a tic-tac-toe board, if anyone did. This is a very, very, very concise way of doing that. So, very clever, very concise. I have to remember it for the future. So there you go. Yeah, really appreciate it. All right, I think that was the last thing I did before I came home. Oh no, I think it was on 75. Let me go 74, see if I can find 74. Filter perfect squares. This is also an interesting question. I didn't really see a much better solution to this as well. I'll explain this one too, what the deal is here. I feel as though I'm spending a lot of time explaining these. A lot of time explaining these solutions and not actually working on it in the next ones, which I guess is okay. Yeah. So this solution, I couldn't really find something better in the solutions, and I'll explain. So it says, given a string of comma-separated integers, write a function which returns a new comma-separated string that only contains the numbers which are perfect squares. So 4, 5, 6, 7, 8, 9, you want 4 and 9. 15, 16, 25, 36, 37, you want 16, 25, and 36. So obviously it's a very small test set, so there's a lot of sort of hacked things you can do, and even less hacked, I guess, if you have very small numbers, not very small, but certain range of numbers where you know the floating point precision is sort of in a relatively manageable range, then you can just take the square root and round to the nearest integer. I believe that's what the other solutions do or did, and I don't particularly like that solution because I forgot why exactly. I guess it's because it doesn't work particularly well for actually, I don't know. Actually, I don't know. I don't know why. I don't know why you wouldn't just round to the nearest integer. I'm actually not really sure. I guess your floating point error would have to be beyond an integer, a single integer, which could happen, I think. But yeah, so I decided not to do it that way, to use the square root function, and I tried to use my own function to determine if it's perfect square, which we've seen this a few times again on stream and kind of recently. You can use a logarithm, a binary search. You can use a binary search to do this, which would be like, as an example. So because if it's a perfect square, obviously the thing that's going to, the square root of it is obviously less than the value of the thing. So you can do a binary search over the range of numbers between 0 and the number you're interested in, right? All the numbers less than that, less than this number. You can, and all you've got to do is just say, okay, pick the midpoint. Say, all right, if I square that, is it larger than the target? If it is, then look at smaller half of the numbers. If it's not larger, then look at the larger half of the numbers, and stop when it's equal, return true. Stop when we've actually exhausted all the values in the range, denoted by the starting point being past the ending point in our recursion. And finally, stop. There's 4 cases when you stop. So stop when you've found the perfect square, return true. Stop when you've exhausted all the values, start as greater than end, return false. And in the other cases, you're going to recurse on the smaller set of numbers or recurse on the larger set of numbers, and exclude the things you've considered already by either decrementing that midpoint or incrementing that midpoint when you're using that value again for the recursion. And that's it. It's really simple. The binary search that you do here. And there's just a little bit of setup here that makes it kind of verbose, and also a wrapper too. But yeah, it's pretty straightforward, and that's just to determine whether or not the value is a perfect square without using like floating point arithmetic or the square root function or anything like that, or rounding. And finally, we do a little bit of string manipulation here. You see this is kind of critical, and I'll explain in a moment. So this resequence, we use any number of digits, right? sequence of digits. So this effectively removes the underscores and creates a sequence out of all the integers we're interested in. And then we map this integer parseInt, which is actually a Java function, to parse the integer for each of the values in this sequence. So because here we just return strings, or we match strings and then parse them to integers. This is kind of important because, like, if I were to remove these, you actually end up with an error, which is kind of weird. But I don't entirely know how to explain that. But it has something to do with I actually don't know. I really don't know at all why. But I found that out, that this seems to work, whereas it wouldn't work if you were to just use this integer, this expression alone. It's really, really odd. So then you filter on the things that are squares, right? Using this function that we've described here, written here, and then finally, what's left over, that sequence, you're going to join with these commas. Sorry, not underscores. Remove these commas, and return that, and that's the end of that. And then that's that. Interestingly enough, this join automatically converts this to a string. This sequence, the result, these sequences. Something else that's kind of interesting here is I was not able to use the I suppose I could have used the last threading macro, and there's also an as threading macro which allows you to use functions where the argument that you're interested in ends up in different positions. You can sort of define the position that it'll end up in. Both of those things, the as macro and the last macro. I could have used the last macro here. The as macro, I think for whatever reason, this like compiler or whatever you want to call it, the environment that this runs the code in, compiles the code. I don't know why exactly, but I think the as macro doesn't work quite properly, and I can show you the as macro as well. I'll show you what it looks like. So here you might have like, yeah, here's the as macro. So you say, okay, bind this to this value, and then the reader is going to the macro, I guess, compiler, I don't know what you want to call it, or the reader will replace, will inform this form. I guess the reader will then be informed of where this argument should end up at each spot. So it'll execute this with the argument here, execute this with the argument here, and then execute this with the argument between these two. So in this case, it's the second argument, third argument. The last argument here, second argument here. So you can kind of mix the last and the second thread, thread first and thread last macros. You can kind of mix them using the as macro. But I think the as macro doesn't work in this environment, which is really annoying. So I could have used the last macro here. I could have, used the last macro here as well, which would have been cool. Let's go to 75 now. Yeah, Euler's Totient Function. So this is the last thing I did before I came home, I think. And we'll explain this briefly. So two numbers are coprime if their greatest common divisor equals 1. Euler's Totient Function f of x is defined as the number of positive integers less than x, which are coprime to 2x. The special case f of 1 equals 1. Write a function which calculates Euler's Totient Function. So the idea here is it's not the number of prime numbers below a certain point, but it is the number of coprime numbers below a certain point. And there's a lot of math involved with the Totient function. It's pretty cool, pretty neat. Euler did some work on it, and there's some explanation on the Wikipedia about the Totient function. It's actually not that complicated, but basically, if you can factorize your number, you can compute the Totient function efficiently. But as we know, factorization is largely inefficient, so it's not that easy. And it's actually the radical that you're looking for. It's not really the it's not the prime numbers that you're interested in. It's the it's not the prime factorization. It's actually just the set of prime numbers that you want, that you're interested in, which is a little bit different. The prime factorization isn't too far off from the set of primes, which you could also consider the radical. I think the radical is actually the multiplicand of all of the prime factors, not including their exponents. But obviously, if you have the prime factors, you can get the exponents rather easily. So yeah, it's excuse me. At least I think it's logarithmic time. You can get all the exponents. It should not be too difficult. So it's which implies that getting the just the prime base, I guess, base factors is extremely difficult as it is, regardless of how much exponentiation you do with those things. How many times those are exponentiated, or how big the exponents are, or small the exponents are. So yeah, so I don't want to write any code. I didn't want to write any code that dealt with prime factorization, because that's a pretty big subject. There's like a lot of stuff that exists, or it's big enough. There's a lot of stuff that exists to factorize to factorize numbers efficiently. There's a bunch of stuff out there. I didn't want to go into any of that, so I said, okay, we're just going to brute force this with a simple GCD function, and we're just going to gather up all the things that are GCD of 1 that are less than x, with a GCD of 1 with x. So we did that, and so I wrote one line for a GCD function. We used the same GCD function that I wrote earlier, which is basically just, you have 3 different options. If so you have A and B are the parameters or arguments. If A is less than B, then swap the 2 and recurse on the swapped version. If the recursion is going to just be place B where A was and use A modulo B, and so we showed previously that the GCD of A and B is going to be equal to the GCD of B and A mod B, which is just kind of interesting, the proof of that. You could think of this as the maximum number of iterations of the GCD of A and A minus B. Yeah, where A mod B would be subtracting B as many times as you can until you get what's left over, and what's left over would be A mod B. You could think of it that way. And so anyway, we get this. So we recurse that way, and then we stop when B is 0. We don't have any remainder anymore, and that means that whatever A was, it must be the greatest common divisor at that point. It's kind of tricky to explain why exactly that's the case, but basically once you've divided evenly into A, you have some amount times B plus 0, and then you're going to try to recurse on that. Well, at that point, that means that A is equal to some constant times B, which means that B is the greatest common divisor, right? Because B would divide A, and so when you recurse on that, though, with B and some remainder, B becomes A, and then the first argument becomes what B was, and the second argument is 0. So that's why you return the A, which is the first argument, which for the previous result would be the B. A little confusing, I realize, but that's super simple GCD, and actually I was able to find that this GCD function is logarithmic with respect to a plus b. It's actually even faster than that, but it's good enough to consider that's logarithmic. Actually, no, it's not faster than that. It's logarithmic, but it's got kind of an interesting function with in terms of the number of bits of a and b. And there's a whole lot of we looked at that the other day. A whole lot of information about like optimizations and the speed of this, but it's roughly it's logarithmic, but it could be faster if you use binary GCD. It's called, and there's some other algorithms too to speed up GCD. But so anyway, so it's fast enough. It's pretty fast though. That's the bottom line. It's fast enough. And then what we're going to do is we just loop over all the elements, commute the GCD with n, right, our input. Excuse me, filter out on the ones that are equal to 1. So all the ones that are not equal to 1, we get rid of them, and then we just count what's left over. And that gives us the totient, sort of brute forced, somewhat brute forced, not exactly, but more or less. And there you go. That's this totient function. Let's try 76 now. I think that's as far as I got. Yeah, intro to trampoline. Okay. Whew. So that only took like an hour and a half just to get us up to speed of what I did today. I'm telling you, man, it takes a lot of time. It takes a lot of time to go through all this. It really does. Truthfully, truly, it takes a lot of time to calculate all of this. Not calculate, but just explain all of it. Explain it. Think about it. Explain it. Yeah. We're approaching halfway through. Also, I think 76. How many problems do we have total? The total problem list is 156 entries. So yeah, we passed. Oh no, we're almost there. I think 78 is. Yeah, halfway point is 78. So we're very close to the halfway point. Approaching it. Getting there. A few more problems. I think today we'll hit the halfway point. So that's pretty good. We're making progress. And I'll be faster and faster at this, I think. There's two things to consider. One, I'll be faster and faster the more problems we do. And two, also to consider is the problems that might get harder, probably. Because I think we kind of start with like the elementary or easy problems first and then work our way up. So the tic-tac-toe problem was the hardest one I think we saw so far. But that one, actually, it was more about being clever than anything else. I mean, I think most of these problems have that kind of, what do they call that, property to them, where it's more about being clever than it is anything else. But yeah, so we'll continue here. So recursion, medium, trampoline. The trampoline function takes a function f and a variable number of parameters. The trampoline calls f with any parameters that were supplied. If f returns a function, trampoline calls that function with no arguments. This is repeated until the return value is not a function, and then trampoline returns that non-function value. Interesting. This is useful for implementing mutually recursive algorithms in a way that won't consume the stack. Okay, I really don't understand what that means. Like, I don't understand why this would be useful for anything. I don't really even know what they mean by this. But, so they're saying, what does this give you? Okay, let function be this thing, this foo bar. And then we're going to trampoline foo with these two arguments. Oh no. Okay. So foo bar. So when we trampoline foo with these two arguments, it says we call foo, which returns a function, right? So we have these x and y, which is empty list and a 1. We conjoin this empty list with a 1, and we end up with a sequence with a 1. We're going to call bar with this thing with a 1 on y, which is a 1. All right. Now, this is a function call. So calls f with any, so it calls this foo. So that means that we're going to call foo means we're going to call bar with this list with 1 in it and 1 as a parameter. So bar is then called recursively, which then gives you if now this would otherwise, this doesn't return a function, this returns a call to this function. This is an anonymous function that it actually calls the function, I believe. Right. Yeah. Oh, I understand. This function is an anonymous function that doesn't take any arguments, but it has this greater context. And what this function does is it actually calls this other function. Oh. F returns a function. Yes, this does return a function. Oh, that is so confusing, but I understand. So this does return a function. The function that it returns is this anonymous function that calls bar with these arguments. Oh, that is so confusing, but I understand. I think I get it now. So this actually does return a function. So when you trampoline, instead of just getting this function, so we could just show you what this will do. Right? We could show this in the REPL. Could also delete all these things. Holy smokes, talk about complicated. So let's do this. Let's define a function foo, which, let's define bar first. Oh, you need reach, oh, all right, well, okay. I mean, all right. Can't really do it without, oh, that's so confusing. Because it's mutually recursive, right? So it's like, can't, yeah. All right. Maybe I want this anonymous function here to be like something that makes some sense, right? Like do something like this. So if you do this, you define this foo, right? And then you say foo of 1. This is a function. See that? Return an object. It's this anonymous function. And look at the name that it gave it. This is an anonymous function. If you now try to call this whole thing, it's got deja vu. You now try to call this thing without trampoline, right? You're gonna get something real interesting going on here. Get something real funky. Now watch this. May cause a problem. No, so you get, so look at this. You get like a function that calls another function, calls another. You do get a function object here, which is, yeah, really funky because it's this anonymous function, which then calls this function, and this function actually refers back to this one. But it doesn't. You don't actually need to know what's in here because it just says this reference bar which exists because we defined it here, and end in the here somewhere is a reference back to foo, which it doesn't actually care. But trying to call this function afterwards is kind of funky. Whereas if you use trampoline, it'll actually call this mutually recursive thing, and then you'll get the desired result, which is funky indeed. Let's see what happens. So if we call trampoline, right? So we get conj 1 1, and then we call bar, which says, okay, if last of x, which is the first argument, if the last of the first argument, which in this case is a 1, is greater than 10, which is false. If it's true, you're going to return x, which is, I think, a sequence, it looks like. Otherwise, you're going to return another anonymous function which calls foo. Right. And because this is trampoline, this anonymous function that returns calls foo with these arguments, but doesn't take any arguments, is just going to get called as well. So then this is sort of your mutual recursion with these things being called back and forth. This calls foo again, but this time with 1, and now y is whatever y was, which I think is 1. 1 plus 2 is 3. So now it's going to be, there's a 1 here, right? A sequence containing just 1, and then this is 3 and 3. So now we have 1, 3. With this 3, we check if 1, 3 is greater than 10. It's not. And we repeat until we'll end up, I think, with 1, 3, 5, 7, 9. And then finally, when you have 1, 3, 5, 7, 9 here, 1, 3, 5, let's see, 1, 3, 5, 7, you can join 9, y is 9, and you say 9 is not larger. So repeat one more time. So actually we'll add 11 here. 11 is greater, so we return 11. Wow. Amazing. Crazy. So I think this is just 11 at the end. Oh no, and it returns x. I'm sorry, it returns x, which at this point is 1, 3, 5, 7, 9, 11. That's my mistake. Last of x. Yeah, return what x is. There you go. So that's fun. Also, like, congratulations, you solved the problem. Huzzah. Huzzah. Alright. So, I mean, I guess they give it a medium because people get it wrong. Like it just did. I forgot that the x is a sequence, and so when you're returning the whole sequence. But yeah, that's pretty interesting. Good old mutual recursion in there. Ye old trampoline. So that's what it means by trampoline. It's like, why they use that word, I don't know, but that's pretty interesting. So Anagram Finder, okay, 77 medium. Write a function which finds all the anagrams in a vector of words. A word x is an anagram of word y. If all the letters in x can be arranged in a different order to form y, your function should return a set of sets where each subset is a group of words which are anagrams of each other. Each subset should have at least 2 words. Words without any anagram should not be included in the result. So you'll have a set of sets where team mat, team mate, eat ends up being meat, team mate. And then veer, lake, item, kale, might, ever. You get veer and ever, and then lake and kale, and item and might. So this is kind of an easy question. I'll describe what you can do. So the way I'd approach it is first loop once through the strings, the sequence, and create a hash map, or actually just create a hash map of No, how do you describe it? No, you don't even have to do it that way. I mean, you can, yeah, okay, you can do it this way. So what you're going to do is, I do it even just looping once. For each string, sort the string and use that as a key in a hash map, right? And then hash the original string to that key in the hash map to a vector. And if there's no vector, create the vector and put that in the vector. If there is a vector, append it to the vector, and do that for each string. And then after that result, with the resulting hash map, you're going to create a set of the. You also actually shouldn't be a vector. It should be a set, right? They want sets, so add it to the set rather than create a vector. Add it to the set, and then at the end, you're going to get the values of, create a set of the values of that hash map, which is these different sets, which basically means drop the keys and convert this hash map to a set. And that should solve this problem in not actually linear time, like n log n, because there's a lot of sorting going on, something like n log n. But yeah, very simple, pretty straightforward problem. I think we can do this in, probably right in the editor, but let's take this test case. Consider this test case here. We'll just define, call this anagrams. It's a pretty easy problem overall. Take S, and what we want to say is, or no, not S, but words, and we'll say, what we want to do is reduce over the words into a hash map, and the function that we want to use is going to be, it's going to take what we want to return, and we want the next word, right? And we're going to say sort this word, and we're going to associate, so that's going to be our key, associate at that key with what's already there. So we're going to ret sort W, so get what's there, or if there's nothing there, then we're going to default to not a vector but a set, right? And if there is something there, then we're going to get the set that's already there. If there's not something there, we're going to get an empty set, and then we're going to actually input into the set. So can we conjure with a set? I think we can. Yeah, well, we can do that in the REPL, I think. Let's do that right now. Set one. And then we can conj. I think conjoin does work with this. I didn't really think about it. I forgot actually. Yeah, I should be more confident that it does work. So we can conjoin with this result the word that we were interested in the first place. Now what we can do is, once we've associated all of these words with this hash set, we can take vals of this hash set and make a set out of that, and we should be done. And that ought to do it for us. So we can, yeah, it's a pretty easy question overall. Right, we get anagrams of this guy, just to check if that's what we want. And we get the arity of number of arguments for associate. That should be 2, right? Oh, and we need ret. Yeah, that's my mistake. Still kind of getting used to the associate function. There we go. Yep. Meet mate team heat mat. Oh, we need to filter out these sets that are size 1. Filter on count is equal to 1. This is also a good candidate for the whatever you want to call that thing. It's also a good candidate for the, that's why it's good to use the REPL. It's also a good candidate for the, also a good candidate for the, what is it even called? The thing. Also a good candidate for the threading macro. That's what it was, the threading macro. I can show you what that looks like, right? Because we've got 1, 2, 3 operations, 4 operations going on here on words. So I can show you what that looks like, the last threading macro. And yeah, let's do that now. So with the threading macro, we end up with something like this. And we want words. And in particular, first we have the reduction we perform on words. Then we have the filter, I don't know, vowels on words. Then we have the filter on what's vowels of vowels of the result, filter on the result, and finally set on the result. Right, we can perform these one by one. And that's a little cleaner in terms of readability. Let me just look at the same thing. Sweet. So now we can decrement here, copy, and run this. And go back a bit. And there we go, got him. Huzzah. Huzzah, not bad at all, not too shabby. Nice, man, nice. Super clean, very clean. Re-implement trampoline. No, I don't want to do that. No, man. Oh, group by they did as well. Group by sort. Oh, that's interesting. Oh, that's effectively what I did. Oh, I should have used a group by. And then they used vowels. Oh, well, actually my set, it was implied here, so I didn't need to use that set command. And they did, oh, now this is interesting. Filter comp sequence rest. Oh, interesting. So filter on compose rest sequence, right? So if this isn't nil, oh, that's interesting. You could do both of these. You could do either of these, right? And then set again at the end. And they used it, made it anonymous. I could have made it anonymous, but I didn't want to. Kind of like to, yeah. I like this though. This is kind of gives you a good sense of what's going on. But yeah, it's basically a grouping. Group by the things that need to be sorted. Uses the sort function as a key, and then everything that matches that key is placed into a sequence. But these aren't sets; these are vectors. So I guess, yeah, I should have used group by. Really, didn't think of that. Frequencies, group by frequencies. Interesting. I don't know what happened here. Group by frequency. Oh, that's interesting. So, oh, wow. Wow. Wait a minute, what? Very interesting. So, I don't know how he figured that, but basically, he used this frequencies function as built-in, grouped by this on strings itself. But the thing that's weird about that is, oh, I was going to say that, oh, wow, it's very clever. Okay, well, check this out. So, I mean, it's not, yeah, it's a little more clever because the sort is a little slower than the frequency, building the frequency map in terms of time complexity. So, although in practice probably isn't that much slower. But, oh, very interesting. So, the frequency map, oh man. So the frequency map of your string is equal to of a string is equal to the frequency map of the other string of its anagram, if and only if it's an anagram. If their one is an anagram of the other, they're equivalent definitions. They have the same frequency map. It's the same thing as calling it an anagram. Frequency map of the characters of the string, by the way, which is why I was confused by this. Basically, it's saying you're going to group by the word. You're going to group the words by the character frequency maps of each of the strings. Oh, very interesting. Oh, that's cool. I'm glad I looked at this. At first I was like, this seems nonsensical, but that makes a lot of sense now. Very cool. You could use the sorted string or the frequency map of the string as the key, which is exactly what he does here. And then he takes the values and then obviously removes all the ones that have single string, and then maps that to a set, and then merges all of these sets into a final set. And that's it. This also would have been a good candidate for the last thread macro. Really interesting. So yeah, a lot of folks use the group by. I didn't use group by. I kind of wrote my own group by. All right, that's probably enough. I think it's probably enough. Cool. So re-implement trampoline to be halfway through it. Medium. I don't want to re-implement trampoline. No, come on. What? No. No. What do you mean? What do you mean? Okay. So, fine. Basically, I think what trampoline's going to do. Let's get this test case. This seems really complicated. I mean, like, it's kind of funny. I was like, yeah, I don't know how it's implemented, but I don't really care. Oh yeah. Now you have to implement it. You're going to be asked to implement it. It's like, oh, okay, yeah, that's good. It's just what I wanted. It's just what I wanted. Okay. So let's define trampoline 2. Trampoline 2. You basically could take all of the problems. So if you wanted to create a C++ library that implements all of the Clojure functions, so that way you could write functional C++. You could you could basically solve this problem in C++ for all of these problems. These are all the implementations of the built-ins using some of the other built-ins. Like you just need, I guess, to copy the Clojure source for C++ for like some built-ins, and then you could use all of these functions as the implementations for the built-ins. Oh my goodness. Okay, so this takes it takes a function f and any number of arguments, and we just want to make sure that this f is a function. And you say, what does it say? Intro to trampoline. Clojure intro, or just trampoline. Yeah. Calls f with the supplied arguments, if anything, if any arguments. If f returns a function, call that function with no arguments. Okay. So calls f with these arguments. Okay. If the result of that is a function, right, then call the result. So let's first just use a let command in here. So trampoline, I guess, is one of your higher order functions that keep going on about. So we'll say result is this function, right? And we say if, no, right, so we only have to call this function once. If result is a function, then we're going to call that function with no arguments. All right. If anything, yeah. If it's not a function, then we're going to return result. Okay. But we're going to repeat this, right? Function is a result, right? So if the result is a function, then we're going to call that function. But we're going to keep repeating this. See, that's the thing that's kind of tricky, is that we're going to recurse. We could write a loop, I guess, but I think what we're going to want to do, technically we can trampoline with no arguments. Okay, I see that we're dropping frames. Uh-oh. 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 Dropping 80% of our frames. May need to switch to the phone's internet connection. All right, looks like we're back, but yeah, let's take this trampoline too and try to run it, see what happens. Too few arguments to if. Oh, that would do it, wouldn't it? Also, I kind of wish I could stop clicking that. Expected 2 arguments, got 1. Can I just nil, you know? Like no arguments? What does variadic recur look like? Excuse me. Almost nil. TLDR for recur call to variadic function, wrap variadic parameters in a list. Single sequence of null should be passed. Okay. Interesting. Oh. TLDR. Okay. So it looks like I was correct. There we go. Trampoline 2 of... So if I want to test this thing, well, all right. Okay. Made kind of a mistake there. Trampoline 2. Let's do it. See what happens here. Okay, no. Nice. Wrong number of arguments, 1 passed to triple. What? Excuse me. Can I do this? Okay. So that works okay. If we try to trampoline 2 this thing, you get a problem. Arity exception. Wrong number of arguments passed to triple. Can we just do an empty sequence, maybe? Can we do this? Oh, that's not good. Oh, man. Excuse me. Well, I mean, we're not supposed to blow this call stack though, right? Like this, we could just do this, but this will blow the stack. No, but we can't. Wait, what? All right, let's start with this. Let's just try this. See, just determine if this is the problem or not. I think this is the issue, but this will let us know. Oh, nice. What? Are you kidding me? Is it maybe, Maybe that's the problem. Maybe I'm just doing it wrong. Maybe that's the problem. True. Hey, we did it. All right, minor mistake here. All right, let's see how we did. Nice. I'm a genius. I'm a genius. I'm a genius. Oh, so smart. Oh, so smart. There we go. Officially halfway through these problems. Whew. Huzzah. Man. How many problems did I do today? Yeah, about 11 problems. 10 problems a day. So that'll take us, if we do 10 problems a day, 156, 2 weeks in a day. A little over 2 weeks will take us. Oh, learning Clojure in a month. It's like, not bad. Not bad. Okay, so I finally understand what, I think I understand what Trampoline does, and even implemented it ourselves, which is pretty cool. Cool. So the idea is very cool. I forgot what I was even saying. So the idea is that you can make mutual recursion a little bit easier without blowing your stack. Yeah, it's kind of cool. It's an interesting, unusual thing. So functions that call other functions that don't take parameters. I don't use mutual recursion too often, but now I know how I can do it without, yeah, quote unquote, blowing the recursion stack. Without blowing the stack. Cool. Cool. Okay. Let's take a look at the solutions, and then we'll go to the triangle minimal path. Although I think all the solutions are going to look similar. Oh, that's interesting. Iterate, drop while first. Oh, that's pretty cool. Oh, I didn't think of that at all. Whoa. That's very clever. It's a function recur. Let RB apply first to the rest. Oh, that's interesting. So this is, he uses, well, okay. Why, huh. Recurs on calling the function. Oh, that's interesting. Why did I need to use nil? Why did that, did I? Oh, because I didn't actually call the function. I'm not sure that I need to though. Oh, there's a loop. Oh, that's probably why. Because he used a loop. I used recur proper. All these folks use loops. This is wrong, actually. So create a stack, more of a stack you don't need. Yeah, same thing. All these folks use loops. You don't actually need to use a loop. Interesting. Am I the only one who did it the way that I did it? I think this is pretty interesting though. This is cool. So this is 1, 2. So 2 arguments, function args, and you say iterate f of n, function f calls f. Which is itself. So you have basically you call the function on the arguments, given the arguments. I think you need to apply this though. This result. Like, why don't you need to apply, right? Given 2 arguments. Like if the function you're dealing with only takes 1 argument, then this works. But actually there should be an apply in here. So I think this is not totally correct. But throw an apply in here in the front, and then this works nicely. So then you have iterate f of this function. So you're going to call this function on this result, and then iterate right on the results of those results. So this would be is a function which takes f and calls f, and this should return a function, right? Which doesn't take any arguments. So then this would be the argument that it takes, and then it calls it, right? And then the result of that then is another function that calls that what that result is, and repeats over and over. So you just keep calling these functions, right, iteratively, and then you drop the sequence. You just keep dropping the sequence until you get something that's not a function. This is a lazy sequence, and then you take the first, what's left over, right, the first value. It's not a. This is really cool. This is really cool. So I'm going to change my answer to what problem was this? This was 48 or 78, I think. Yeah, I'm going to change my answer to apply this guy. Oh. Oh. Yeah. Yeah, so I think this is what you should have. But slightly different syntax. Should do the same thing, but it did right, because trampoline could have a variable number of arguments. So this is so cool. So triangle minimal path. Next one. Hard graph theory. Write a function which calculates the sum of the minimal path through a triangle. The triangle is represented as a collection of vectors. Path should start at the top of the triangle and move to an adjacent number on the next row until the bottom of the triangle is reached. So I think this problem you can solve using dynamic programming. And you can write, I think there's a few different ways to solve this, but I think the way I would like to do it is to use use dynamic programming, use a, what do they call that? Kind of like a backtracking algorithm, recursive backtracking. It's memoized. So I think this is the first time I'll probably use memoization in Clojure. And Clojure does have a memoization like built in, which is pretty nice. But I think the way you would do it is something like this. It's like, excuse me. 1, 2, 4. So we have 1, 2, 4, 5, 1, 4, and 2, 3, 4, 5. So what you could do here is, just making sure if anyone said hello, just say hi to them. What you could do here is, if this path, right, and then you probably want to take the, now what's interesting is that this path branches and then this path branches, right? That's the path. So then this path branches. Yeah. Assuming you can adjacent number on the next row until the bottom of the triangle is reached. I want to say that, I want to say it's the other way around. I want to say it's, let's go all the way back. Clearly one can only go to 2 and 4, but I think you're only supposed to go straight down and to the right as your possibilities. Right, so each of these positions have a, like I guess a choice to make. Now the thing is, this isn't that difficult. You could do a dynamic programming solution that says like 1, and then obviously you have to use 1, so you can do 3 and 5. Then from here you end up with, you can either do 8 or add a 1, which gives you, so it's 3, you can get 8 or 4, right? So you could do it this, I don't know if that's correct though. Actually, I'm not really sure. If you take the minimum at that point exactly there, right? 3 you can go to 8 or 4. If you take 4, and then 5 can go to, excuse me, 6 or 9. And then obviously you could throw the 9 in there. I think what you want, it's not what I just showed you, it's 3 or 5. I think, so to get to this 5, yeah, I think this is the correct way to do it. So to get to 2 is only 3, to get to 4 is only 5. To get to 5, you can do 3 to 5 is 8, or you can do 5 to 5, which is 10. So 8's the best here. Then to get to the next value, 1, you can go 5, 6 to get here, or you can go 3, 4 to get here, right? And then to get to the third spot, you can go only 5, 9. Ah, yes, that's what you're supposed to do. You're supposed to say, given this position in the triangle, what's the optimal path to get to that position? And then obviously you can generate the next set of optimal paths if you have the previous paths. Yeah. Kind of interesting dynamic programming solution. A little more obvious than the other ones. But you could call this something recursive, which is like, basically you'd say, find for the I and ijth, like given I and j, find the optimal path to that particular, from starting the starting point to that particular position. And then you can just take the maximum of all of the bottom positions. And then finding the maximum up to that point requires only knowing the, I mean, that's like the inductive, but there's a way to do it that's recursive though, and memorize on that recursion. There always is. Like the logic is straightforward, but How do we show that? How do we think about that? At each, yeah. So the recursion would actually be looping through all these I and j positions and memoizing the results. And so you would say it's I and j would be parameters to the function. And basically, yeah, you would end up finding out what all the the optimal paths would be for each I and j. And for a given ij, you need to know, you basically choose a minimum of the previous two. That's kind of what you end up doing. Right, there are only two ways to get to that. Only two, there's one or two ways to get to that particular spot, and you're going to take whatever's there plus the minimum of those previous two. So that's actually where the recurrence comes from. And you just memorize on those two previous spots. If there aren't two previous spots, obviously you just take the one that's there. Yeah, pretty interesting question. You can do this using somewhat more concisely using, I guess, a reduction, because you can. Well, I think memoizing the function is actually one of the best ways to do it. I think it's probably the simplest. Writing recurring function, or just a recursive function that's memoized, I think is the right way to do it. We'll do that next. I don't want to do that now, but yeah, that's how you solve it. Obviously, it's especially pretty simple. You just take, so for this next spot, 8, 4, 9, right? You've got 2, so 2 is required. So you can do 10. It's the only way to get to 2 from right, from 8 to 10, and then you can do for 3. You could either go 5 or 1, which is 8, or 4 to 3, which is 11 or 7. So you take 7. Then you get this 4. You can either go from 4 to 4, which is 8, or 4 and 9, which is 13. So we'll take 8. It's the smaller of the two. And then finally 5 at the end. You have to go from 9, so you go to 14, and then clearly fastest is 7 here. 1, 2, 1, 3, 7. So you can do the same algorithm on the other side. So yeah, pretty. When I was younger, I had solved this problem, but it took me a very long time to understand it, like why this solution, how this comes to be. Now I understand it. It's very simple, very easy. I have a much better grasp and sense of dynamic programming, quote unquote dynamic programming. It's basically all dynamic programming comes down to is some recursive solution that you memoize, and that's really it. You can pretty much almost always, I don't really know exactly why, but almost always. Well, I think I know why. I do know why. I shouldn't say I don't know why. I do know why. You can pretty much always just describe it as a recursive function and then memoize that for the parameters. And that's it. That's it. I think I could probably prove it, but I'm not going to do that now. We'll come back to this later. So, kind of don't want to, I don't know, for whatever reason, I don't want to just keep going endlessly. I'd rather just stop and, I don't know, go to bed, relax here. So yeah, thank you again. Thanks for watching. Talk to you all soon, and have a good rest of your day. Take care.